Hello, Bapat.
Yeah, yes.
Hello, sir. Good morning. Bapat, are you able to hear me? Unmute is low. Are you able to hear me? Phone വിളിക്കണം. Hello, Bapat. Are you hearing me? Okay. Fine.
Oh, yes.
Bapat, are you hearing me?
Hello? Yeah, I'm unmuted. I'm unmuted. Yeah. Yeah. Can you hear me? Yeah.
Good morning to you all. We'll begin the first plenary lecture of this conference for today by Ken Kawarabayashi from Japan. I invite Professor R.B. Bapat of Indian Statistical Institute, New Delhi, an eminent algebraist and an author of a well-known book on graphs and matrices. And I invite Professor Bapat to conduct the proceedings. Over to Bapat.
I'm happy to welcome you all to this session. So let me introduce the speaker. It is Professor Kenichi Kawarabayashi. Just to give a small introduction, he is at the National Institute of Informatics in Tokyo as Deputy Director. His research interests are in discrete mathematics and theoretical computer science, more specifically graph theory, combinatorics and algorithms, scalable algorithms, combinatorial optimization, and its application to machine learning and theoretical analysis of deep learning. He's on the editorial boards of several journals, just to mention a few: on Journal of Graph Theory, Discrete Mathematics and Theoretical Computer Science, Algorithmica, and Graphs and Combinatorics. He has received several awards, for example, the IBM Japan Science Prize in Computer Science in 2008, Japanese Academy Medal 2010, and Mathematical Society of Japan Spring Prize 2015. So he will talk today on directed graph miner. So I welcome Professor Kawarabayashi and request him to give his talk.
Thank you very much. Thank you very much for introducing me. So can you hear me now? Is everything
Yes.
okay? Thank you.
Yes.
Now let me start sharing my slide. So slides okay now?
Yes.
Thank you very much. So thank you very much for inviting me to speak here. I think all the people in India, good morning. Here it is like 1 p.m. now, but I think that we have only 3.5 hours difference, so we're almost the same time zone, and I'm happy to give a talk here. So today, I'd like to talk about directed graph miner. This is joint work with a couple of people, most closely Stefan Kreutzer. This is trying to extend the graph miner project for undirected graph to directed graph. So let me begin with importance now. Firstly, structure theory, or sometimes structure graph theory, and tree views is very important in this graph theory community. So structure theory based on the tree views and the tree decomposition, or excluding grid miner or graph miner theorem, is very successful, and most notably in graph miner theory. So in this talk, I meant that the structure theory basically means the graph miner. And tree views and tree decomposition is not only important in graph theory, but also outside the graph theory as well. In the graph theory, this plays an important role in graph structure theory, namely graph miner theory. This is a key to prove important theorem in the graph miner. Not only the graph miner, but also algorithm. There are many algorithmic applications on graph class of bounded tree width graph. Bounded tree width graph means the tree width is small. In this case, for example, graph coloring, you want to color the graph with the optimal color. This is an awfully hard problem in algorithm, but if you know that the graph is small tree width, this is solvable. This creates a lot of many algorithmic applications on the graph class worlds, and I think that this means that tree width is also important in algorithm. And if you are interested in logic, monadic second order logic is also very closely related to tree width and tree decomposition. So you can see that tree width and tree decomposition is very important, not only graph theory, but also the algorithm, logic, and many others. You may not know what the tree is and what the tree decomposition is. You don't have to worry about this because I'm going to tell you about this in 1 minute or 2 minutes. Okay, now let me talk about a little bit of structure theory. This is a picture of a structure theory in the sense. Let me put the two things. This is basically describing a graph miner theory. It starts with trees, and then people look at the planar graphs, and then previous banded graph. That means that this is extending the tree a little bit. Then what happening is that if you are not with a small tree with graph, then there's a big theorem called grid theorem, and that sort of separates the world below below and above, and the below, in algorithmic sense, you can do like dynamic programming and divide and conquer. This is two of the most important algorithmic tools in this world. And if you're interested in graph theory, what every exposure property is sometimes very important in the graph theory, and that's also hold in this world. But by the grid theorem separates the world that the exposure is not true, and also this world graph algorithmic techniques, unfortunately, dynamic programming and divide and conquer they're not directly applicable. However, we have to do the structural graph approach here. This is based on the structure result. What's happening is that if you have a big grid miner, then either you get the big click miner, or otherwise this click miner, grid miner start capturing the surface. So you can see that the grid structure graph theory, mainly graph miner, begin with the trees and tree decomposition, tree views, and that's also important algorithm application. So I would first talk about this part of the thing more precisely and more detail. But the main focus is not actually undirected graph. I will present what is so sorry to go back to the picture. I will talk about what the trees is and why it is important. Trees is so important. But my main purpose of this talk is to actually extend to diagram. Things I talked about so far are basically the undirected graph, but then if you go for the directed graph, so things are much harder. So that's why that is something I'm working for many years, like 5 to 6 years. So that purpose of this talk is basically to report my progress and future direction of many questions. All right, so here is the content of my talk. I will again define the tree Wilson graph minor in the next section and then extend to diagram. So that's two things that I will talk about in the next 10 minutes. So, but before that, I would like to talk about a little bit of a more graph minor because what we are doing for directed graph is basically following the path by graph minor approach by Robertson Seymour. The big goal is that to figure out the structure without a big H minor. Basically, that graph minor project can be divided into several steps, let's say 7 steps. And the first step is what as I talked about, basically tree views and how the what is why it's important to tree views. And then you go to grid minor theorem, and that's sort of a separate word I mentioned. And these two will be important in this talk. And I'm going to talk about undirected case, maybe the graph minor case, and then I will talk about the directed graph case because that's much harder. Okay, so this is a step that I'm following. We are following because we are following to extend the graph minor project by Robertson Seymour to the directed graph. Okay, so this is a picture, and what I said about is basically the first step is this part in the previous picture, in previous step, the step 1 here, and the step 2 is here, and the step 3, 4, 5 in actually this part, which I think I don't have much time, but I will talk about it a bit. All right. Let me begin with the trivials because this is the most important concept in graph minor. And Trevis is right now very famous. If you have a distilled graph theory book, it's already there. So I'm not going to give you a precise definition, but if you are the outside the graph theory world, I will give you intuition of what the Trevis is. Let me a little bit go on that. So just look at these pictures. So this is a tree like this with the colors like blue and red and green and yellow. And this is a graph. And then the tree is that you start from some tree by blowing up each vertex to some vertices. And the previous is that how many vertices you sort of blow up, a maximum size or how many times you blow up. For example, this graph, blue correspond to this triangle, red correspond to this red triangle, and the green correspond to here, and yellow correspond to here, and red correspond here, and the blue correspond here. And Trevis is for some reason it's a -1 here. So but essentially the definition of Trevis is how close to the tree, and if you say Trevis K, it is obtained from some tree by blowing each vertex by K vertices. So that's the definition of tree views. And I think that if you want to get more detailed, please refer to the distilled graph theory. Now, importance of a graph, tree views is that it's a great structure graph theory I will talk about a little bit. And again, that algorithm many have NP hard problem can be solved in linear time even for the fixed small tree views. And logic, again, the monadic second order, and general, it's also using the AI or database data mining, or sometimes social network and program language as well. So this concept is not only important in graph theory, but also algorithm on the general database, data mining, AI, and so on. So that's the importance. Now, so far I talked about trees for the undirected graphs. What about digraphs? That's the next topic I'm going to talk about. Okay, so here is a fundamental question I like to address. What is the tree width for digraph? And later on, I will talk about the minor of the digraph. But first, let's look at what's the tree width for that directed graph. Tree width for undirected graph goes like this. If you have such a graph, right, then you sort of decompose this graph into like first 1, 2, 3, and 4, 5, 6 by deleting 1, 3. So the tree width basically say that you want to break the graph into small pieces, and then sort of to blow up like this. So that's a fundamental way of understanding a tree width for undirected graph. But directed graph is a little bit different. Let me just skip it a little bit. So it's analog except the following. So if you look at 1, 2, 3, and 4, 5, 6, right? And if you want to divide 1, 2, 3, and 4, 5, 6, maybe you want to cut 1, 3, or 4, 5, or something like that. But for directed graph, you only need to 8, because from this 1, 2, 3 to 5, 6, 7, 8, you can go from the 1, 2, 3 to 5, 4, 6 of if you using like this edge with this part, this edge to this edges. But you can't go to the 4, 5, 6 to from 4, 5, 6 to 1, 2, 3 by if you delete 8. The point is that I'm only talking of weak separator, which means that it's only separate one direction. So in the tree decomposition here for directed graph, you may talk about the separation, but it's only talk about if it's only delete one vertex, which basically cues one direction, but maybe you have a opposite direction. Now, why do we care about this? So analogs, let me go back a little bit here. So that this is a precise definition, but the intuition of the directed tree width is here. How close to a DAG, directed acyclic graph. Remember, for the undirected graph, the tree width is a measure of how close to the tree. But for directed graph, the correspondence of tree to the directed case is essentially directed acyclic, right? So we want to measure the graph how close to a DAG, and that measure would be the directed tree width. Again, let me just repeat again. For the undirected tree width, this is a measure how close the undirected graph to a tree. But for directed graph, this is a measure how close to a directed acyclic graph. Indeed, the directed acyclic graph is directed acyclic graph is directed tree width is exactly 1. So the directed tree width is again how close to the DAG, directed acyclic graph. So this is a fundamental difference. For the undirected tree width, this is undirected graph how close to a tree. For undirected graph, this is a measure how the directed graph close to a DAG, directed acyclic graph. So that's important intuition. Okay, let me just skip this part. So here I talked about the tree width for digraph. It's a measure of how close a graph to a DAG, directed acyclic graph. But I'm not talking about minor for digraphs. That's I like to talk about right now. So for undirected graph, we obtain a graph H by deleting a vertex, deleting H, and contracting H. Then we say the graph has an H minor, right? So important thing is that the minor operation, the deleting a vertex and deleting H and the contracting edges. For the directed graph, the definition of the minor is very similar. So you can actually say that deleting a vertex or deleting edge, that's same. However, contractions are a little bit tricky. So why the contraction is tricky? Let's look at this picture. This graph is totally acyclic. You can't really have a cycle, but if you contract these edges, you suddenly get the cycle. So that's a bad definition because the contraction is supposed to preserve the property of the graph. For example, this graph is acyclic. There's no directed cycle. But once you start contracting these edges, you get a cycle. Then it's not acyclic. So we don't really want to kill the original graph property after you contract the edges. So the good definition right now, it's accepted by many, is the following. A minor operation, you can contract the edge only if only ongoing edge is just one. So if you look at this vertex, this is only a single edge going out, and all other edges are in. Or opposite way, there's only one edge is in, and uh, only one edge is in, and all other edges are out. So this is one case, like right. So there's only one edge is out, and only edge, other edges are in. So that's in this case you can only contract the edges. Why do we say this is a good definition? Well, because the point is that this contraction never create a new cycle, right? There's no there's no cycle that go like this way because this edge is like this direction. The only cycle can go like this direction, and this edge contraction of this edge doesn't change existence of the cycle. So the point is that I can only contract the edge which preserve the property of the graph. And in this case, the important thing is that you can't really create a new cycle. And in this way, the only safe way is that either only outgoing of only one edge is outgoing, or only one edge is incoming. That's the only case that you can contract the edges. Again, so this is a definition of a minor, and this is a bit of different from an undirected case, because undirected case you can contract any edges, but for the directed graph you can only contract the edges when only one of the edges going out, or only one of the edges is going in. So that's a totally different thing. Okay, so that's the definition. Now I'm going to talk about the next step. All right. What I have talked so far is step one of the graph minor for undirected graphs, and then I said that basically this part can be extended to the directed case. So down for the diagram. Let me just remind you that we follow the same line of the graph minor project. Okay, so that's why we want to follow this steps 1 to step 7, and the talk, the stuff I talked so far basically clarify the step 1 for the undirected graph, and then we extended the diagram. So basically step 1 is done. Now I'm going to talk about step 2. The step 2 is the grid theorem. This is a big step, and it was mainly of the graph minor 5. Oh, by the way, this GM means a graph minor. You know that there are 23 graph minor papers, graph minor 1 to graph minor 23, and that's appeared here. So far, we look at the graph minor 1 to graph minor 4. Now we are going to look at the graph minor 5, and we extend to digraph. That's what we are talking about in 1 minute. And for this picture, it's actually this breaking point to go above if this process is true or not, or dynamic program divided control works. So that's the big step. Okay. Now for the undirected graph, the main result of the graph minor 5 by Robertson Seaborg is what is called the grid minor theorem. This is the following. For any R integer, there is some function f of R such that for any graph, either tributes of at most f of R, or you have R by R grid minor. So you have like R by R grid minor here. And the original proof is like this is huge, but then the Robertson, Seymour, Thomas, and the Diestel, they show that basically it's an exponential band, and keep going. And in general, 2012, that me and Kobayashi and even Seymour, they is a little bit better. But right now it's actually the polynomial band. Now, what is the importance of the grid theorem? Firstly, this is a polynomial band, that's important. Now, second thing is that if you work on the combinatorial optimization, this grid minor is very important because this is a good structure for using the routing. And if you work on the fixed parameter tractability, this is one of the most important tool in the fixed parameter tractability. So the discrete theorem is important, not only the graph minor theory, but also many algorithmic application and the combinatorial optimization as well. So here is let me just emphasis again. It's a bond between the existence of R by I grid minor and the trivials. That's the grid theorem. Right. Now I'm going to talk about what about directive grades. And in fact, the first thing I have to clarify is what is actually the grid for the diagram. This was actually suggested by Nogaron, Bruce Reed, Robertson, Seymour, Thomas, 95. They said that this is the grid minor. Why this is the grid minor? Now, first look at this grid minor. It's actually you have a cycle, same direction the cycle, nested cycle like this. And from the inner cycle to outer cycle, you have an alternating path. This is going out, this is going in, this is going out, this is going out. The reason why they say that this is the right concept is that okay, I think I forgot to mention that the one of the things that the important thing about the grid minor is this grid R by R grid is 3 with R. So we want to make sure that this grid minor must be the 3 with at least R or something like that. For the diagram, this structure has a directed tree with at least K actually. So in our definition, this tree is also so big as well, and this is globally connected in a sense, and most important in many cycles. So they came up that this is the right concept of the grid, and we want to show this. So they've conjectured that the function such that every diagram of tree with at least f of k has this grid minor. Again, let me just remind you that you can only contract the edges if the only one edge is going out or one edge is going in. Now, the history is that they showed like 99, it's true for minor planar graph and the minor free, and then something happening. But we worked on this conjecture for many years, and finally we made it like 2015. Me and Stefan Kurtus shows essentially the same thing. So either you get like tree decomposition, directed tree decomposition, or you always get this great minor. So that's a directed grid minor theorem. So again, let me just put this picture. As I said, the grid minor is really the start point for the graph minor project to show this very important structure theorem. And this is also true for algorithm application. The grid is important. Now, here it's a little bit, we go look at the directed case. This is an undirected case, this is a directed case. We came up with at this level so far. So I think that this is a big achievement because that's the first step to go beyond the bounded trivial graph. But of course, this is not the end of the story. What we want is that as the graph minor project by Robertson Seymour suggests, can we go further? Right? Can we go further means that this picture from their grid theorem, they start getting either a big click minor or they have a almost embeddable graph. This is beyond most important structure theorem graph minor. So what they did is starting from the grid theorem, they get the famous structure theorem, right? Now the question is, can we go further? Can we go the same thing like extend the graph minor theorem? So that's what we really want to do. Or maybe what about the application of the grid theorem? As I told you that in the undirected case, there are many algorithmic application? Do we have the same thing for the direct graph? That we want to work on a little bit. And this will be actually true, but I can only talk on in 10 minutes or something like that. So the next couple things I'd like to talk about is more progress using the directed grid theorem. As I told you that we are down with step 2. So the first half of my talk is about step 1, and I defined that I present to you to define the tree views for directed graphs, and that is in terms of that is how close to the deck. And the second step, I said like a graph minor 5 is a big step for the graph minor project, the grid theorem, and large tree views imply big grid minor, and that's also done for digraph. Now, can we go further step 3 and step 4, 5, 6, 7? That's what we are working on now. And what we can do is only step 3 and step 4. So next 10 minutes, I talked about a little bit of 3 and 4. First, for some technical reason, let me begin to step 4. For the step 4, the graph, this is a result of graph minus 13. What does this say is that if you start with a big grid minor here, then either you get H minor, or otherwise you can find some part of the grid minor here. So copy it here, so that this part is flat after deleting small number of vertices here. What is a flat? That is the following. Flat means that for the directed graph, it's a planar graph. So the definition of flat is the following. If you look at the grid minor and the graph embedded inside, and you take a corner, opposite corner A1 and A2, and diagonal called B2 and B1, you don't have a path between A1 to A2 and B1 to B2. So this is essentially two-path theorem, what is called the two-path theorem. And these two decision paths A1, A2, and B1, B2 exist. If you assume some connectivity, then it does exist, except for the following. You have a planar graph here. This, you can think of this as a disk embedding all the graph embedded in the planar way. And A1, A2, and B1, B2 goes appear like this. In this case, there are no two decision paths from A1, A2, and B1, B2 because A1 to A2 path is basically divide the B1 and B2 because this is a planar graph. So this is obstruction, and that's essentially the definition of flat. So this theorem tells you that after you delete small number of vertices, this grid minor essentially induce a planar graph. And that's important in the graph minor project because this is the base of the rest of graph minor structure theorem. So they have a very complicated but a deep structure theorem, but the starting point of this theorem. And moreover, all the graph minor algorithmic application use this one. So this is so important in the sense that if you're interested in algorithm, and this result is enough to show something, for example, disjoint path or minor testing, and this is an important step in the algorithm as well. Not only the algorithm, but also graph structure graph minor result. What we do, we essentially extend this result. Namely, if we start with a big grid minor, we get like this kind of structure theorem. But there are a couple of difference, actually big difference I have to tell you. Again, the graph minus this is a flat. But what does this flat means in the directed graph? Do we have a two disjoint path theorem for undirected graph? This is no, and in fact, this is probably hard because if you are familiar with the directed decision path problem, even the directed two decision path problem is NP complete. So if you see that this is an NP complete problem, then it's almost hopeless to get the exact structural theorem. But what we can say, we only say that there is no disjoint path. There's no disjoint path from here to here and here to here, no cross. And this part is only the bounded trivials. That's the only thing we can say. And we also say that it's a little bit weaker one. We can't say that subworld to satisfy, but we can perform in polynomials. Let me just summarize it. So what we can show is that very close to the undirected case. But if you start with a big directed grid minor, then either you get like H as a tournament minor, unfortunately, or there's a wall which may not be here, actually somewhere. There's flat. This means that it's not, sorry, this is not quite near planar. This is just says that only there's no cross path like that. So that's what we can say. So this is, sorry, this near planar is false. It just only says there's no cross like that. And moreover, we can perform to find such a structure in polynomial type. All right, so that's what we have done so far. So this is somehow the step 4 I've talked about a little bit. The very brand new result I would like to talk about in the next couple of minutes. It's step 3. That is called canonical tree decomposition. But this is very hard to mention the exact result. So, and if you look at the graph mine 10, that's also hard to read. So I like to only look at a picture to tell you what means. It's a tree decomposition, but if grids are separated by some small separation, they are going to be the different back. And moreover, this edges actually correspond to a separation. So that's a canonical tree decomposition, except that it's not quite as strong as an undirected case, but for our purpose, this is enough. So I would say that this part is done for digraph. So in the last couple of minutes, I talked about step 4 is done. And now I talked about step 3 is almost done. I said done, but I should say it's almost done. All right, now you may wonder, like, can we go further, step 5 and 6 or 7? That's what we are working on right now, and I can't really say any progress for example, step 5 at the moment. And step 6 is even much harder. We are not yet done. We are not there, but I hope that we will be there quite soon. Maybe in not quite soon. Maybe in a couple in a year or something like that. So that's a progress status from undirected graph to directed graph. The last 5 minutes, I'd like to talk about applications. So at the beginning of this talk, I said that the undirected graph minor project by Robertson Seymour is so influential, and that there are many applications, not only the graph theory, but also the algorithm or many other computer science area. We found a little bit the application, so that's something I really talked about right now. One application I like to talk about is about the Younger's conjecture, which was proved by Reed, Robertson, Seymour, Thomas, 96. This theorem tells you the following. There's a function f of k such that for all digraphs and k, either this graph contains k pairwise vertex existing directed cycles, or there is some vertex set which has a size at most f of k such that if you delete t, then it's acyclic. In other words, this vertex t is a hitting set for cycle, because after you delete that, this is acyclic. This is actually very close to the thing that I mentioned, Erdős-Pórsche property. Erdős-Pórsche property means that there is a function f of h such that for digraph and k, either you have a k copies of h as a subdivision or minor or something like that, or you have some vertex set of f of k vertices such that after you delete s, then it doesn't contain h as a minor or maybe subdivision. So this is a special case when the H is just a triangle cycle, right? Because it's a capable of a directive cycle. Now what we can do is that this kind of H here, H copies H is copied the directed Erdős-Pórsche. This is only if H is strongly connected. This is only possible when the H is a part of the grid theorem. So in particular, if H is a cycle, then this implies the Younger's conjecture as well. So what we show is that this would follow our theorem by using the grid theorem. So I think that this is still under it's still a little bit annoying thing about the strongly connectivity. It may be possible to extend to something weakly connected, but we don't yet go yet. Okay, so this is an application by Porsche. Another application is another Porsche property again. We can borrow the half integral Porsche for the odd cycle. What is a half integral? Half integral means that it's not disjoint. For example, this theorem tells you that either precise treatment is that either you get the k odd cycle such that every vertex uses at most 2 of the vertices, or there's a vertex of set of order f of k such that after you delete this vertex set, then the graph is bipartite. And unfortunately, this half integral needed. You can't really make it Porsche property. The second thing I like to mention is that this here is Bruce Lee's result for undirected. He also showed that this for the undirected case. And unfortunately, this is actually needed because this is an even grid cycle, even grid minor. And if you add H's in the diagonally, then you can't find the 2 decision cycle. But in order to kill all the odd cycle, you really have to delete actually 1 row or 1 column. So that means that you really have to delete all the vertices here, which is like square root of n vertices. So again, so this theorem tells you that you need a half integral, and that's also true. That is also needed for the undirected case as well. And the final thing I'd like to talk about algorithm application. So because our proof is constructive, there are a couple of algorithm applications. The most notably I'd like to talk about is the direct decision path problem. So decision path problem is the following. You are given the graph and 2k vertices S1 to Sk and T1 to Tk. Can you find the disjoint path from P1, P to Pk such that Pi is from Si to Ti for any I? So this is like going like this. You have a given this S1 to Sk and T1 to Tk, and you have to find a path from S1 to T1, S2 and T2, and so on, Si to T2, Ti, sorry. So that's a problem, but I think that we have to ask that each vertex is using at most twice. Why do we need this statement? Because we already know that it's going to operate even for k equal 2k's. If you want the disjoint path, then this is only even the NP if S1, S2, and the T1, T2. Only you can't find the 2 disjoint paths. For the undirected case, if k is fixed, then it's P by graph minor project. So the best we can hope is this is like needed. What we can do is that we can't really prove this, but what we can do is that to figure out the k decision paths do not exist or half integral exists. So this is a bit of weaker because what we want to show is actually only this one to decide it, but we can't. We only do the k decision to don't exist. So either it is a certificate that you can't find the k decision path like that. S1 to ST1 to ST. Otherwise, sorry, we can find half integral. That means that it's actually this one. We can find P1 to P1 path so that each vertex is used at most 2 of them. And we can only do this one. And one thing I have to tell you interesting is that if you have a big grid minor, and if you also have a terminal S, which is S1 to Sk, and the k decision path from S2, discrete minor. And if you also have that terminal set T, T1 to Tk, and the k decision path from the grid to Tt, then you can find the half integral path, because like this is a k decision path here and the k decision path here, so the vertex outside the grid is used at most twice, right? This path and one of the this path from S to the grid minor, and one of the paths from the grid minor to T. And inside the grid minor, you can sort of do the routing. So that's one of the things. This is actually the best situation I'd like to state. So what we can do is that only this one, either the k-decision paths don't exist or half integrate this. This actually use algorithms the grid minus cell and the canonical Trinity. So we need all the things so far. But let me just summarize my talk, but actually to go a little bit more. We talk about half integration paths, and this is the best we can do. And what we have is a very weak one, but I think that it must be possible that this must be doable. More, each vertex is used in at most 2 of them. So this is much stronger than our stuff, because we say that we can't really decide this, but we can only say that decision path doesn't exist. So this is one algorithmic question. And back to this picture, in the directive case, we are basically down from here, from up to this level, the grid minor. And in the graph minor, from the grid minor to get like a structure theorem, that's a lot of work. But what we want to do is we really follow their line of the work to get the similar structures of the directed graph, and that's what we are doing right now. So again, we need a step 5 to 7, and that's still a lot of things. You can see that it's like graph minus 7, 11, 12, 14 to 17, 13 to 22, 23. These are not yet done for directed graph. So that's part that we really have to do right now, and we're working on that. We hope to present the progress quite soon. Other stuff what we can do, again, the extend the graph minus theory to digraph, that's what really we are doing. And again, the more use of the grid theorem or maybe some other stuff is probably interesting in algorithm, but we don't yet get it. And finally, there is a polynomial time algorithm for half integration paths. So that's what I mentioned, that this problem, you are given the graph and the k vertices S1 to k and another k but T1 tk. Can you find the distance by P1 to pk so that pi start Si and Ti, and moreover, each vertex in the graph is used at most 2 of them. Now, this is probably the most difficult, the most important problem in the directed decision path problem. Okay, I think I'm done, and this is 45 minutes talk. I think. Thank you very much for your attention. Let me stop sharing.
Are there any questions or comments from the audience? You can unmute and ask directly. Yes. Is there a question? I just want to ask for the half integral disjoint paths problem. Is there a Menger type theorem?
Sorry. So what is the question now? Half
For
integral?
the half integral disjoint paths problem,
Yes.
is there any Menger type theorem? That means max min.
Well, the Menger type theorem is from S to T.
Yeah.
And you don't specify the Fitch vertex called Fitch vertex. That's basically same as the Menger. So that does exist. From S to T, you find the k disjoint path. That does exist.
Okay, but that is for disjoint paths, not
disjoint path. Yes.
Okay.
But the other difficulty is that we specify one guy to go to the specific guy. That's a hard one.
Okay.
So want to ask any questions, you please ask directly to the speaker. I think somebody wanted to do that. Venkatesh?
No.
Participants in the muted. Hello?
Okay, I think don't see any questions.
Hello, any questions? What a point now, right?
Okay, so since there are no questions that I see, let us thank the speaker for the very interesting talk. Thank you very much.
Thank you very much.
Thank you, Professor Bapat and Ken Kavarabayashi for this session. And the next session will start at 10:45. Plenary talk by Ritabrata Munshi to be chaired by Professor Kalyan Chakravarti. So we'll at 10:45. Thank you.